the field of statistical physics, and at the turn of the millennium, there's this burgeoning field of network study, and Réka was one of the maven and one of the master of that field, and I keep doing work on that topic, and that has been very inspirational. And it's particularly striking because Réka has moved towards using Boolean models to try to study the dynamics and to try to learn some very detailed understanding. I come from systems immunology, and there were some models of immune responses which were very nice in terms of using Boolean models to really infer stuff, but also more meta properties of networks. So I hope it will be kind of a grand view of network biology and a very good keynote. Thanks.
Thank you very much, Grégoire, and thank you for inviting me. It's really great to be here. I enjoy this conference a lot, and I'm excited to tell you about my group's research. So as a grand overview, my group is collaborating with wet bench scientists in developing predictive models of biological systems, and this can be signal transaction networks, gene regulatory networks, the immune response, as Grégoire mentioned. So we are developing these models because we want to understand how these systems work when they work well, how they can go wrong, and if they go wrong, how we can correct and put them on the right path again. So all of this is collaborative. So in the meantime, while we were doing the construction of these models, and it's about 10 to 11 models now constructed de novo, we realized that we also need our methods to become better. So we did some method development. And so I will focus on the method development, and I will use it on a most recent network model that we developed. So as a kind of a motivation, which I think is probably familiar to you, but just to give you the background. So we know that networks, signal transaction networks, gene regulatory networks, metabolic networks underlie cell behaviors, like cell motion, proliferation, programmed cell death. And here's just an illustration out of many possible illustrations of chemotaxis and the signal transaction network that governs chemotaxis. And when there are mutations and deregulations in elements of these networks, that can lead to wrong cell behaviors, and wrong cell behavior can lead to disease. So this is a very nice review paper by Ravi Iyengar, where they show and illustrate how different mutations and deregulations, and they have their four or five different types of such deregulations, can impact proliferation in cancer. So we know that the effects of these deregulations propagate through the network. They are not localized to whatever is deregulated. And so I want to say that a better understanding of the cascading effects of these deregulations will help us better understand how we can control the disease, or how we can mitigate the damage caused by the mutations, and ultimately can lead to therapeutic strategies. So we connect these networks to the outcomes by dynamic modeling. So what is a dynamic model, and what are the steps involved in it? So first we need to determine and construct the network that's underlying this. So this can be a signal transaction network, a gene regulatory network, or something that includes both, because usually that's the case. There are external signals, but there is also gene regulation. It's very important that this network needs to have directed edges, and these edges need to be either interactions or causal effects. An undirected network, unfortunately, is not very suitable for this kind of model. Then we characterize each component by a state, and this can be a continuous variable, or it can be a discrete qualitative variable. And then we will also characterize each component by a regulatory function that tell us how the state of the nodes varies by the interactions that they participate in, by the effect of their regulators. And the very crucial point here is that we can relate the long-term behavior of a subset of the nodes, so it doesn't have to be all the nodes, to the cell behaviors, to the phenotypes. And in some cases, only a single node, which